This talk has been prepared because I was giving a talk at a conference in St. Andrews. I just 5 minutes ago changed this because I realized it still said St. Andrews. Well, the point is that that conference was Harmonic Analysis and PDE Meeting, it was the name. And so I kind of needed to make it like more accessible, less sort of metric stuff and details. And so this is like the form of the talk as I'm going to give it here. It's a bit more of a broad introduction into a notion of how you can measure sort of number of directions that there are in a set and where it comes from, what are some interesting results you can prove using this or you can prove about it. And it's kind of a hybrid between a sort of a broad overview talk and a presentation of my own results. Most of the time it's the broad overview, but at the end I do some of my results, and these results come from a joint work with these three people, so that Giovanni, David and Andrea. Of course the names will be stated when I state the theorems that we came up with, but also keep in mind this is still a work in preparation that's not on archive, should hopefully relatively soon be. But I mean, if you want some details, you're going to have to write me or David an email. So let me just tell you, the structure of the talk is very simple. I'm going to tell you about like two notions of some sort of like a dimension or a tangent or the number of directions you have. These are Alberti representations and weak tangent fields, and then I'm going to show you what you can do with them basically. It's very simple. So I'm going to have some conventions. So for the entire talk, X is a complete metric space and everything is appropriately measurable. So I just wrote, there are some parts where measurability is not an entirely trivial thing to solve, but I'm just not interested in that, so I'm going to like assume that everything like that can be solved. Most results are already interesting in if X is a Euclidean space. Some of the results we only have for X being a Euclidean space. All of those pretty much work in uniformly convex Banach spaces. It's just a bit more annoying to state them. So, you know, like if you're interested in anything that locally looks like Rn, the results will follow. The moment you're interested in anything that has a sufficiently round norm, the things will work. Really sort of the issues are the moment you know, you have a norm where there is a piece of straight line in the unit sphere. Okay, so without further ado, the broad idea of what I'm going to talk about is that we have a set S and we wish to attach to points in S linear spaces tau x, such that, broadly speaking, curves in S through X can only go into directions of tau x. Now this is not a revolutionary idea because, I mean, you can probably find a 60-year-old differential geometry book that defines tangents to manifolds, broadly speaking, in this way. We also wish to apply this idea to measures instead of sets, which is entirely non-trivial, like what I mean by that, because like what are points inside a measure, right? However, trying to apply this to general sets, like you don't assume any structure of the set. S is literally a metric space, and that's all you know about it. That is somewhat of a newer idea, and the question is, where does it come from? Which philosophically can mean two different things. One is, where did a person, a human being, came up with this thing for the first time? I am not, take it with a grain of salt, I was not able to verify this by speaking to the relevant people, but my understanding historically is that people are studying differentiability of Lipschitz maps. And when you study differentiability of Lipschitz maps, you realize very quickly that, well, Lipschitz maps are differentiable along curves. And if you study this for like a really long time, it starts sort of looking like that's the only sense in which they're differentiable. Of course, in Rn, the moment you're differentiable along like all curves, somehow you automatically upgrade to better notions of differentiability, like the Frechet differentiability. But it really, inside the proof, it really comes down to having the curves. Now, more broadly speaking, you might not be interested in where people came up with it, but where it comes from, sort of more objectively or ideologically. And here I have like a list of things where this appears. So if you're studying metric current, I'm not going to tell you what these things are, but basically the biggest open question concerning metric currents is whether every metric current is a Federer-Fleming flat chain. And if you study this for a while, you can characterize this statement in terms of these types of tangents, which exists in a paper by Giovanni Alberti and Andrea Marchese, so you can look that up. Another thing is, if you want to characterize rectifiability and pure unrectifiability, you can do that using these notions, or this type of an idea. Lastly, and this is sort of the content of the joint work that I have with David and Andrea and Giovanni, is if you're interested in like Hausdorff measure or dimension of a metric space and how rigid it is. So maybe I have a metric space that has a high dimension, but maybe I can just perturb it slightly and then it has a very low dimension, which is a thing that can in general happen, and you're interested in when can it happen. So before I define actually these types of tangents, I'm going to just define what rectifiable means, which everyone who has attended the winter school at the beginning should know. So a metric space which is complete, assume that like an ambient metric space is complete, as I said before. We have a subset, we say that the subset is unrectifiable if you find countably many subsets of Rn and Lipschitz maps from these subsets into X such that the images cover almost all of E. And a set is called N purely unrectifiable if it intersects E in a set of measure 0 for every unrectifiable set E. So the reason I'm defining it is because these two types of sets will be our basic examples. And so things to keep in mind, right? Something like this, possibly with some dust. This is one rectifiable, right? There's a bunch of curves. That's not so hard to understand, but two examples of purely unrectifiable sets I want you to keep in mind are the four-corner Cantor set, which you obtain by taking the unit square in R2, partitioning into 16 pieces, keeping the 4 squares, throwing everything else away, and then you do it to every square again, right? And you continue infinitely many times, and in the intersection you get something, some set K, and funny thing it satisfies is that it has a finite positive length. So it's like a very nice one-dimensional object, but it is, of course, one purely unrectifiable. And another thing is the Koch snowflake, which I'm sure everyone has seen. So the dimension of this guy, let's call this guy S. The Hausdorff dimension of this guy is less than 2, but bigger than 1. It's a number. And it is also one purely unrectifiable. This is not entirely trivial to prove because there is a curve, right? But the curve is continuous and it doesn't have any Lipschitz pieces in it. So if you take any Lipschitz curve in R2, for example, the intersection with this set has always measure 0. It's not entirely trivial to prove as far as I know. But I mean, it's not like you can give it as an exercise to like a very smart student and they're gonna figure it out. And one big thing to sort of see is that this is very disconnected, which is kind of what you expect in the purely unrectifiable case, and this is very connected. So this is maybe a little bit counterintuitive, and this is allowed to happen precisely because of the dimension here. If you have a one purely unrectifiable set of finite length, it has to be totally disconnected. So you can't have it needs to just sort of be very diffuse. But at the moment you drop that condition, that doesn't need to happen anymore. Okay, so now I can define like the first notion of a tangent. First, I'm going to need to consider Lipschitz curve fragment. So any bi-Lipschitz map from K to X, where K is a subset of 0, 1, which is compact, is called a Lipschitz curve fragment. Of course, if you want to think of K, right, if you take K as connected, then it's a curve. Here, really, the qualitative difference is that K can be, for example, totally disconnected. What you want to think of typically is like a fat Cantor set, so something that has positive measure, so you can't forget about it, but it is so disconnected that you can't define a curve. You can only have a curve fragment. So the set of all of those Lipschitz curve fragments is denoted by µ-a.e.x, and it is equipped with some distance. So each graph of these curve fragments lives as a subset of x times 0, 1. You can put a product metric on that. That will induce a Hausdorff metric, and that's what this is. If you don't know what these things are, just think of it as like a slightly weaker notion of uniform distance. So two curves are very close if their domains are very similar, and on the domains their values are uniformly close. So at every point they're close. Now, what is a d-dimensional weak tangent field? Let's first do it for a subset of a Euclidean space, because it's a bit easier. For a subset of a Euclidean space, the d-dimensional weak tangent field is any map which to each point of E attaches a d-dimensional subset of Rk. So this is the Grassmannian. And the condition you needed to satisfy is that for every curve fragment through E, if you look at the direction of the curve fragment, it's actually traveling inside this tangent tau, and this must hold for almost every t in the domain of gamma. A few things. You really require this for every gamma. So there is no notion of null families of curves in this case. And secondly, if you have a tau which is a weak tangent field, and then you define a tau tilde which is strictly larger, for example, at every point, right, you have a d-dimensional weak tangent field, and at every point you choose a direction that's not in there, you include it, you create a d+1 dimensional tangent field. It is still tangent field because you just made the right-hand side here larger. So like this is completely non-unique, and it's just one directional inclusion. The moment you have a d-dimensional weak tangent field, everything larger is also a weak tangent field. So generally you're interested, what is the least d for the given set E, such that we have a d-dimensional weak tangent field. An example, a set like this has a one-dimensional weak tangent field. Because on these points you take this copy of R, and these points you take this copy of R. Of course that doesn't work here, but that's just one point. So it's a null set on any curve. This set, right, the square, has a two-dimensional weak tangent field. You need to sort of attach all of R2 at most of the points. You can maybe take like a point where you attach something smaller, because it's just one point, it doesn't matter. If you take for your metric space, let's say, the whole thing, right, as a disjoint union, then, right, you can still attach a two-dimensional space here and it works. It is kind of stupid. But for the whole space as a whole, you need two-dimensional tangent field, because this guy needs two-dimensional tangent field. Now you can of course like stratify the space, cut it into different pieces that require different dimensional tangent fields, but generally we'll be interested in sort of the least d that you can get this done for. Okay, so more general examples. If you have n dimensional manifold, then it has a d-dimensional weak tangent field for every d, because they're not equal to n. Clearly for d equals n, you just take the tangent field, the like smooth one, and then for every bigger d, you just attach to it whatever direction you like. Right, more generally, as I said before, if a set E has a d-dimensional weak tangent field, then it also has a d+1 dimensional weak tangent field. For rectifiable sets, it gets a bit more complicated. So if E is n rectifiable, then what's easy is that you can find a null set, n, which is null, and such that the remainder of the set admits an n-dimensional weak tangent field. That you can kind of do simply. The question whether you can remove the set n, I'd rather not talk about. Yes, if the set E has positive measure, then you cannot do anything better. So you need at least an n-dimensional weak tangent field. Nothing smaller is possible. So that behaves as you would expect, right? For purely unrectifiable sets, it's a bit more complicated. In the dimension 1, like, it sort of works nicely in that a set is one purely unrectifiable if and only if it has a zero-dimensional weak tangent field. The reason for that is if you're one purely unrectifiable and there are no curve fragments, no non-trivial curve fragments, meaning the condition in the definition of weak tangent field is trivial. So you can just literally attach the zero-dimensional vector space at every point.
So is E here not the images of the Lipschitz maps?
Sorry, what?
Is E the images of the Lipschitz maps? Or how do you find E? So if you are in rectifiable, sorry.
Oh, sorry, yeah, there is a if missing. So there is, no.
Sorry, that's for the third one.
Yeah. So what?
Is E the images of the Lipschitz maps? Sorry, no, E, sorry. So how do you find the N?
So every rectifiable set can be written as a countable union of bi-Lipschitz images of subsets of Rn and a null set.
So these.
Throw away the null set, and for the bi-Lipschitz images, it's easy.
Okay. Yeah, that was
because you just sort of take them. Yeah, and so for the other direction here, so if one pure unrectifiable, then zero-dimensional weak tangent field, I just talked about that. Vice versa, well, the only way you get to attach a zero-dimensional thing at every point is if there are no curves. Like, otherwise, there would be a piece of curve that would have to go in some direction, in at least one direction, right? So here it is quite easily equivalent, but in higher dimensions, the notions actually disagree. But you still have this. So if you have an n purely unrectifiable set, which also has a finite HM measure, this is very important, then you can find a null set that you can throw away, such that again the remainder admits an n-1 dimensional weak tangent field. As I said it here, it's already highly non-trivial. All of these things also make sense in a metric space, except for, let's say, one, so I'm talking about manifold. All the other ones make sense in a metric space, and they hold in a metric space. And the 0.5 actually gets much harder in a metric space as well. In fact, you need just a recently published paper by David Bate and Julian White to actually state it in this big of a generality. So I can't get into the details, and whether in this case you can forget about the set n, that's completely open, as far as I know, other than if you're in R2 and n equals 1, in which case you don't need to remove the null set. Yes, so as I told you before, these things make sense in a metric space, so I should probably tell you how you make sense of the weak tangent field in a metric space. And the way you do it is, not only do you have a subset of a metric space, but you also have a Lipschitz map into some Rk. Here you sort of want to think of F just being completely arbitrary and Rk being maybe very highly dimensional. A d-dimensional weak tangent field with respect to F now is any map that is the same as before, except we've changed the condition here. Instead of gamma prime being in the direction of the tangent field, we require f of gamma prime to be in the direction. So the way this looks on a picture is you have your metric space X, you have a curve fragment gamma, you have a map F to some high dimensional Rn, and here you maybe have F after gamma, and the sort of tangent you attach at this point, it needs to respect the direction of the curve inside Rk at the image of the point under F. Also, this is sort of also as a side note, this is different from looking at just the pointwise image, so looking at the set f of E and then constructing the weak tangent field there, because you could have a bunch of things which are not curves get collapsed by f into something that's a curve. So you could get more curves in the image. And then what we do is we simply say that the set E admits a d-dimensional weak tangent field if it admits a d-dimensional weak tangent field with respect to every Lipschitz f into every Euclidean space. Which means we of course don't construct anything. Like, it's not like there exists a d-dimensional weak tangent field. We just say that it admits it, and it's like a slightly strange language. I'm not claiming that I can construct one. And I definitely can't construct one that works for every f. Obviously, it has to differ from f to f. Okay, so I think the next is, yeah, so now I have defined a notion of a weak tangent field for subsets of metric spaces. I've told you some basic properties of what it does. And now I'm going to come back to what I was talking about in the beginning, and that's the fact that we can do this for measures. And actually for measures it sort of looks more technical and more complicated and more sort of mind-boggling. But it turns out that once you actually sort of get used to the definitions, everything is just so much easier when you work with measures, to the point where in fact most of the interesting things have been solved for the measures and almost nothing has been solved for these set-wise things. The reason being, if you have a measure, you can throw away a null set, and that's just insanely powerful. So the way this is done for a measure is we start with the definition of an Alberti representation. So if we have a finite Borel measure mu on a space X, we say that a finite Borel measure here on this space of fragments, right? So there is a metric here, so I can talk about Borel measures. This is called an Alberti representation of mu if I have this expression. So let's unpack it. Here I have some absolute continuity. You can just think of equality here if you get confused by absolute continuity. It's just for technical reasons. You can think of equality here. And what is this measure here, right? So this should be a measure. This is a measure that takes the set E, looks at its intersection with every curve fragment gamma, calculates the length of that, and then integrates that quantity against this measure eta. So this looks maybe a little bit like the Fubini theorem, right? Because if I have my unit cube, unit square equipped with L2, and I have a set E, one way to calculate the measure of E is to look at all of its intersections with curves which are just the straight ones that go horizontally. You calculate the length of each of them, and then you integrate against like the Lebesgue one-dimensional measure in here. Obviously, this Lebesgue one-dimensional measure can be injected into all the curve fragments. It's just going to be supported only on these straight ones. And so this generates an Alberti representation of L2 on the square. The measure eta just calculates, well, a measure of this set of curve fragments that are here is the length of this guy. And the measure of any set of curve fragments that are not straight going from left to right is just zero. We can say that that's zero. We just ignore them. Now, of course, there can be much more general Alberti representations, and there is like many different geometrical ways to think about them, right? Like there's like a funny way where you can find two Alberti representations of the unit disk, which kind of pretend to be the polar coordinates. You can find a representation that goes over these guys, right? And then you can find a representation that goes over these guys. Like multiple different ways to disintegrate the L2 on this. Also, you can just take these guys, or you can take these guys. That's a huge non-uniqueness in how you can do these things. However, in some sense, right, you want to think, for example, on the square, that there kind of are only two Alberti representations. Because, I mean, the measure sort of really looks two-dimensional, so we need a way to say Well, let's say I have this Alberti representation going from left to right, and then I add the second one that goes from bottom to up. I want to kind of say that in some sense there are no other Alberti representations, and the sense is something like whenever you give me another different Alberti representation, it's just in some sense a combination of these two. In the sense of like a vector space, right? Obviously in R2 there's infinitely many directions, but you only need two to obtain all of the other ones just by linear combinations. And so this is what happens. If we have a multiple Alberti representation, eta1 up to eta d of µ, and now I'm just going to work directly in a metric space, so I'm going to fix a map from a metric space into Rk, which is Lipschitz. This map kind of plays a similar role as in the previous definition. So we will say that these eta1 up to eta d are F independent if I can find independent cones C1 up to CD. So C1 corresponds to eta1, C2 corresponds to eta2, etc. And then what happens is that if I look at the direction of gamma with respect to F, I need to stay in the cone Ci for eta I almost every gamma. So now I'm not working with every gamma, but only for every gamma inside the Alberti representation. And then, of course, for only almost every point in the domain. Right? So, for example, if I take this to be eta1, this representation, and this to be eta2, these guys are independent with respect to identity. You can take this cone for this guy, and this cone for this guy, and you can take the cones arbitrarily thin as well, because they're very straight. So we will say that representations are independent if you can find some f such that they are f independent. And you can verify that if you are in a Euclidean space, this is true if and only if f can be taken as identity. So there is no better map than identity in Rn, but if you're in a general metric space, there is no such thing as identity, and so you need to just say that there exists an f. And again, this counts number of directions, right? This, instead of counting the number of directions in which there are curves, it's counting the number of directions in which there are measures over curves. So on eta1, to be nicely defined just on curves going inside a beautiful cone, so they just keep going in one direction, more or less, and then I can have multiple of those directions, and I calculate the maximum number of those. And converse to before we had, if I have a d-dimensional weak tangent field, I also have a d plus 1 dimensional. Here, of course, if I have d-independent Alberti representations, I also have d minus 1, because I can just throw one away. So these two things are going against each other, but if we're working with measures, they are related. So let's have a measure on the space X, and let d1 be the maximal number for which I can find some set E of positive measure, such that when I restrict to that set, it admits d-independent Alberti representations. The reason I need to restrict to a set is I could be in this setting, and my measure could be h1 on this guy plus h2 on this guy. That doesn't have two independent Alberti representations because of this guy, but if I forget him and just keep the square, I have two independent Alberti representations. So I'm sort of I'm trying to find the largest piece, the highest dimensional piece. And we can do the opposite, so we can take d2 to be the infimum of the set of those d for which I can forget a null set, and the remainder will admit a d-dimensional weak tangent field. So this is kind of similar to how you define the Hausdorff dimension of a measure. It's the least dimension of a full measure set, right? So here we're looking for the least dimension of a weak tangent field of a full measure set. And these guys are the same number. So if we're working with a measure, kind of what we want to study is this, and if we assume that we have this, it is very simple to prove things. It is very difficult to prove that you have this. However, if you are working with a measure, it's generally quite easy to prove this. And then you can just throw away the null set and you get this. So that's kind of why it's easy to work with measures, because finding independent Alberti representations is somehow simple. Okay, so I have not told you anything interesting, right? I've told you some definitions, how they're related. Why should you be interested in these things? Oh yeah, sorry. This quantity, the same quantity, I will call this the tangential dimension of mu, and denoted by this dim t of mu. So what can you do with these notions? What kind of interesting results can you prove? So that's in the applications. We can construct a thing using Alberti representations. This thing will kind of measure locally how many independent Alberti representations the measure has. So the thing we construct will sort of be one-dimensional here and two-dimensional here. This thing is called decomposability bundle. It really should be called something like a tangent bundle, but this is the name that was designed for it. So this is due to Giovanni and Andrea. It's a bit of an involved definition, but maybe we can get through it. If I have two mu measurable maps from Rk into Gk, these are all linear subspaces of Rk, so any dimension you like. We write that v1 is less than or equal to v2 if v1x is a subspace of v2x for mu almost every x. That makes sense. This defines an order, a partial order, on the equivalence classes of such maps. So the equivalence is standard. Two maps are equivalent if they are equal mu almost everywhere. And what you can prove is this. So v mu, which is an instance of a map such as this, is called the decomposability bundle of mu if it is a minimal mu measurable map which satisfies this condition, which should look exactly the same as the one we had for weak tangent field, right? So for every Alberti representation, if you look at almost every gamma, the direction of gamma has to be in this tangent, in this vector space that I have attached at that point. And this, of course, must again hold only at h1 almost every t in the domain. The thing is that when we had this for sets, we had for every gamma. Now we have it for every measure over gammas, which is an Alberti representation of mu. So this is kind of every curve in mu. Really, what you're talking is every Alberti representation of mu. And so this is kind of, okay, I have these independent Alberti representations. Now I can kind of think, okay, if I am in Rk, I can actually attach tangents so that the Alberti representations actually go in the directions of those tangents. And now why the hell do I do this? Because it characterizes differentiability of Lipschitz maps. So what happens, important, the bundle exists and is unique mu almost everywhere. That's like the hard part to show. The moment you have this, you can prove this. Every Lipschitz function on Rk is differentiable in every direction of the decomposability bundle at almost every point x. And secondly, you can't do any better than v mu. There exists a Lipschitz function on Rk which is non-differentiable in every direction which is not in the tangent bundle at almost every point. So this is like Rademacher kind of on steroids, right? In one direction. This tells you somehow that, this tells you this, right? If you have a finite Borel measure mu on Rk, this is supposed to be three statements, the following three statements are equivalent. Every Lipschitz function is differentiable mu almost everywhere. It's the same as the dimension of this guy being k, right? Because we know we are differentiable v mu with respect to directions in v mu, and being differentiable means you're differentiable in all directions. So v mu has to be the whole thing, which is the same as v mu having the same dimension as Rk, which is k. And you can quite easily show that this is actually equivalent to being able to decompose mu into countably many pieces, and each of them has scale-independent Alberti representations. So you in particular characterize for which measures you have the Rademacher's theorem, for which measures can you differentiate almost everywhere. Now, as such, it's not particularly useful because neither of those is a very nice condition. But this was fixed later, kind of, by De Philippis and Rindler who showed this, that if you're in this situation, so if you have k independent Alberti representations, then you're actually absolutely continuous with respect to the Lebesgue measure, which means that this gives you weak converse to Rademacher's theorem. If a measure mu in Rk is such that every Lipschitz map is differentiable mu almost everywhere, then mu is a subset. Mu is absolutely continuous with respect to Lebesgue measure. So differentiability of Lipschitz maps characterizes those measures which are absolutely continuous. This is called weak converse because strong converse is something like if you have a null set, then you can construct a map which is non-differentiable everywhere in that set, and that's a complicated and much more difficult problem. So this is called a weak converse to Rademacher. Not to say it's a weak result, I mean this paper is really, it's in annals, so I mean, it's a pretty good paper probably. Okay, so here you could kind of see these types of questions are where the Alberti representations came from. And now I'm gonna sort of finish by telling you a couple of definitions and results, which are more closer to just studying these objects directly as opposed to solving different problems using them. But we will see at the end, by just changing our point of view, that we've basically resolved also like a problem that kind of looks to be of independent interest somehow. And so what we're going to do is, instead of studying differentiability of Lipschitz maps, we're just going to look at general properties of Lipschitz maps. Why should we study just differentiability? So what we will do is we will take this space, a given metric space X. You can study all the one Lipschitz maps into Rm, and for technical reasons they will be one Lipschitz and bounded, and then you can study the structure of this space depending on X, right? And the theorems you would want would be something like, well, if X has some properties, then this space has some properties, and if this space has some properties, then X has some properties. Standard thing. Why do this? Well, differentiability doesn't really make sense in a metric space, and also, I mean, even in Rk, you can be interested in other interesting properties of Lipschitz maps, just other than being differentiable, right? What will be happening in practice is that we will be showing density of some sets of functions. So let's say you give me a function and a property, and I want to approximate that function with a sequence of functions that have that property. And the way this is done is, well, you have your starting function and you just change it slightly. The way you want to think about it is you perturb it. And so what we'll be doing is constructing perturbations of Lipschitz maps. And so the way you can think about this is, like, this is the space of all perturbations somehow. The method to show density will be bare categorical. So I'll just remind you what that means. I will need a metric on this space. So I will equip it with the metric induced by uniform, by the uniform norm. Then the resulting metric space is complete, which is very useful because we can use it for bare category theorem. So we recall that a subset of a metric space lambda is called residual if it contains a countable intersection of open-end sets. And then we have the bare category theorem, which says that if lambda is complete, then any residual subset is dense. Which means that you can think of residual subsets as large, as being large. And we'll use this language. I now realize probably you've seen some of this in David's winter school talk, but I'm not sure everyone was here. So a typical function f, we will say that a typical function f satisfies some property p if the set of maps satisfying p is residual. So it's kind of like almost every, just a different version of it. Yeah, and then sort of, I would say, kind of the first result in the direction of showing something really interesting about metric spaces via these perturbations is this paper by David. So again, this is a result a lot of you have seen before. If we have a set which has positive finite Hn measure in a metric space, then it is n purely, if it is n purely unrectifiable, then for every dimension you want, if you look at the typical map into Rm, we will see that it carries the set E into something that has measure 0. And of course, the other statement also holds that if the set is unrectifiable, then for every m larger than n, a typical function satisfies the other thing. So you can characterize pure unrectifiability in terms of these maps, right? So a set is n purely unrectifiable if and only if you can achieve this. Because if it is not n purely unrectifiable, then it has a rectifiable piece, and that rectifiable piece will cause this problem. It's a characterization of pure unrectifiability. Where do the tangents come from, right? Well, the point is, there is just no way to prove this without using them. Not that I know of. I don't think anyone knows of this. If there would be a person, it would be Sylvester, right? Yeah, so this rectifiable part, you don't need the theory I introduced, but to prove this, like, it's just, you need this, like, it's so, like, embedded inside the proof. The idea is so much based on it that, like, I really can't imagine how you could begin proving a statement like this without using these notions. So that's, like, another reason why they are quite useful. Of course, if you know the Bezikovich-Federer projection theorem, then this is like an analogous version of it for metric spaces. There's like a few things you can think about here, right? So what can we do? You can ask about improving this theorem. Some of you have seen that this guy can be improved. If E actually lives inside a Euclidean space, then instead of a zero, bigger than zero, you can get equal to Hn of E, which is kind of counterintuitively strong result, but it holds. I've talked about it like 3 months ago. The question that I'm going to be interested in is like, how can you improve this result here? Of course, you can get a smaller number than zero, but what you might think about is, what if we don't have this finiteness assumption, right? So for example, this guy is one purely unrectifiable, but it doesn't even have a sigma finite H1, right? Because it has higher dimension.
Yeah, so I'm trying to understand this first statement. For the Koch snowflake, it says that map is extremely atypical.
No, it just doesn't hold, right? Because the snowflake doesn't satisfy this.
Oh, sorry, okay.
Right? So that's the point, yeah. This does not apply to the snowflake because snowflake has infinite length. I mean, it applies to sigma finite length as well, but snowflake doesn't have a sigma finite length. It applies to the four-corner Cantor set.
Mm-hmm.
But actually, let's look at the four-corner Cantor set, right? I'm going to show you like a sequence of maps that you can construct. Let's say you have a F1, and that just goes from the unit square, and it just maps everything to a point. It's a constant map. Right? Then you take F2, and that guy looks at the first iteration of the set, and it maps each of these guys into a point, which are correctly spaced so that F2 can pretty much look like an identity inside and still be one Lipschitz. It means it has to squash a little, because if you squash all of these points, then in order to be one Lipschitz, you then have to move everything together a bit, but not by too much. And you keep doing this process, so F3 will go from the second iteration, and I'm not going to like draw the whole thing, right? But it will map into like, you'll have 4 points here, 4 points here, 4 points here, 4 points here. And again, you just scale everything so that it's just barely one Lipschitz. And it turns out when you calculate sort of the distances between the guys, it turns out that Fn uniformly converge to the identity. But this is a very strong result because Fn, maybe I should call them Fi. Because now, if I take Fi of E, not only H1 of Fi of E is 0, but they are finite sets. So not only do you get 0 length, you actually get finite, which is just infinitely better, right? Of course, you can't get finite for a residual set of maps, so for a typical map will not be finite. But what you can get, at least for one purely unrectifiable set in R2, in not too much work, if you know all of the sort of results, is that in fact you can get that the dimension of f of e typically will be 0. Not only will h1 of it be 0, meaning that it is at most one-dimensional, but in fact it will be 0-dimensional. So you can reduce the dimension by one whole number down. So you can do that. I'm not sure how you could do that in higher dimensions, because sort of it's a bit tricky to prove it generally. Of course, for some nicely structured sets, you can just do it by hand. And okay, so then the second question is, okay, we can maybe get this squashing into finite sets, but what can we do? So that's like one way to improve this. Instead of getting like h and f of e being 0, we would want the dimension is less than or equal to n minus 1. That would be much stronger, right? Another thing we might want to try is remove this condition, but we can see that completely fails for the snowflake, because except for constant maps, the image of the snowflake is a connected, non-trivial space, so it has positive length. So you can't do anything. And the results I'm gonna present kind of combine these two problems and solve them both at the same time while simultaneously sort of not solving either one of them, because they sort of, the two changes you do sort of help each other. So the result we can get is this. If X is a complete space and you have a separable subset of it which admits a d-dimensional weak tangent field, then for every finite Borel measure mu on S, the typical F will satisfy this. So the push forward of the measure under F will have Hausdorff dimension at most d. Just so you don't have to unpack the definitions in your head, this means that for a typical F, I will find a subset N which will have 0 measure, such that the remainder gets mapped to something that has that dimension less than d. Maybe if you're not used to working with these things, it might be a bit difficult to connect this to the previous theorem. So I'm going to look at some examples. The best one is the snowflake. So I know that a typical map cannot push forward the snowflake into something 0-dimensional because of what I just told you. However, this theorem tells you that you can give me your favorite Borel measure on the snowflake, it doesn't matter what it is. And then for a typical map F, I will be able to forget a null set, and all the rest of it will be mapped to something 0-dimensional. So if I allow myself to forget null sets, and it's in a meta way, like in any way you want, right? You can give me any Borel measure, I can do it. Of course, the most natural measure is like the self-similar measure you can put on it, and for that it works, obviously. It's a measure, right? So what happens is kind of counterintuitive. If you have the Koch curve in R2 and mu any finite Borel measure on it, then a typical one Lipschitz map simultaneously does two things. It maps mu almost all S into a 0-dimensional set, which is what the thing above says, because in this case d is 0. But the remainder has to be mapped into a set of dimension bigger than 1, because the totality of S must be mapped into something of dimension bigger than 1. Constant maps you can forget about, they are a small set, so they don't matter. So big things get sent to something like not only small, but like ridiculously tiny, like 1 dimension lower. And the remainder realizes all of the other stuff.
So this is again saying that the standard embedding is very atypical?
Standard embedding does not have that property, yes, so it is very atypical. Of course, this holds, so yeah, if you think of S intrinsically as like 0, 1 with a Fermi metric, then yeah, like sending it with a map into R2 in a way that doesn't do this horrible thing is very atypical. Of course, this is a bad categorical argument, so usually the typical behavior is the worst possible. So like I can't construct a single map that does this. I can prove that there are plenty of them. I can't construct a single one. And of course, this argument holds for any non-trivial path connected to purely one another rectifiable metric space, which of course immediately path connectedness implies that the length is not sigma finite. Okay, so the reason this doesn't like resolve either of the problems from what I was talking before is that, of course, like I do need to allow myself to forget null sets, otherwise I can't do anything. So the question from the previous theorem, if you want to remove the finite measure assumption, you can, but you can't work with sets, you then have to work with measures, right? So in this theorem, if you don't want to have this, then you have to replace hn with something else. But of course, usually when hn of E is not sigma finite, then E will naturally have a different measure on it, right? Natural measures are usually finite or sigma finite. And this question of whether you can get dimension reduction, well, we can get it up to a null set, right? But of course, this gives you the same thing. Up to a null set, this is empty. So like, once we allow ourselves to throw away null set, whether you can push forward f of E into something of small dimension becomes entirely trivial. And so it doesn't solve this problem. It doesn't. But it's still like a very nice measure theoretical statement, right? Like if you're not interested in sets, but you're interested in measures, this really gets you everything. Another question you could ask now is this optimal, right? So let's say, what would optimality mean? It would mean, well, if S admits a d-dimensional weak tangent field, but not a d-1 dimensional, so d is the best I can get, can I then construct a Borel measure mu such that for a typical f, I will actually get larger than or equal to d, right? Then I would, in combination with this, I will get equality. We can kind of do that. There are two problems. First, what we do here is we use the fact that since S has a d-dimensional weak tangent field, every Borel measure mu on S has at most d-independent Alberti representations. To flip the statement, you would need to show that if S has d-dimensional weak tangent field and d is optimal, then you can construct a more Borel measure mu on it which actually attains that number, which is a non-trivial statement. We don't know how to prove that. So when I show you the other statement, it will not be in terms of the weak tangent field, but in terms of Alberti representations. Secondly, we can't do it in a metric space. As I said, the problem with general metric spaces is this: if you have a norm that's not round very much. So I will state it just in Rn, even though, as I said, it works in uniform Banach spaces. And so what you get in Rn is this. If you have a finite Borel measure in Rk, which has a piece with d-independent Alberti representations, and you look at maps into Rd, so this is the same d as here, then you will find a non-empty open set of maps which realize the maximal possible dimension, because we are going into Rk here. Now, because it is open and non-empty, it means its complement cannot be dense, which means it cannot be residual. So it is kind of a converse to the other statement. Now, can I combine these two statements into one in a way that makes everything a lot more easy to understand? And the answer is yes. And I actually really like this. I only realized this after we had all of the results, that this is what happens. But you have like a really nice characterization of Hausdorff dimensions in Rk. The thing that happens is this. For a measure mu in Rk, you can define the stabilized Hausdorff dimension. So here we have a set, and we're not interested per se in its Hausdorff dimension, but in the least Hausdorff dimensions to which we can squish it without changing it too much. And this is defined rigorously in this way. So we take the least S, such that I can find a sequence of one Lipschitz maps which converge to the identity uniformly, such that each of these maps squashes mu into something of dimension at mod S. So this is a stabilization of the Hausdorff measure. Because this guy, by the theorem 2 slides ago, right, like if mu is any measure on this guy, then this stable guy is actually 0, although the Hausdorff dimension is bigger than 1. So Hausdorff dimension is just not stable under these types of operations, right? You can perturb the measure arbitrarily with an arbitrarily small perturbation in this sense, such that you push it forward to something lower dimensional. And it turns out that because we're in RK and we have the previous result and the one and here, you actually can show this. So this stabilized Hausdorff dimension actually just counts the number of directions in which there are curves, which is what this dim t of mu does. So reminder, dim t of mu is like the maximum number of Alberti representation that the piece of the measure has, or alternatively, it is the least dimension of a weak tangent field of a full measure subset. And it is kind of strange, right? Because, I mean, when we were going into this, we were thinking kind of along the lines of characterizing some Hausdorff dimensions. It was more like looking at the previous theorem and ask, can we squish things somehow more efficiently or whatever? And this is just like what turns out that you get out of it. One remarkable thing, there doesn't seem to be any reason for why this should not be fractional. Like, I mean, this guy, Hausdorff dimensions can be fractional. Why should this guy be an integer? Well, it must be because of this. And I actually don't know any easier way to show that it is an integer. And I mean, this is quite difficult. You have two big theorems in that paper, and this needs both of them. Otherwise, you can't get it. But yeah, remarkably, the fractional part of the measure always gets lost in these perturbations. So the fractional parts are always sort of invisible to Lipschitz maps. You can always squish them very, very efficiently. Okay, and that is everything. Thank you very much.